In this tutorial, we will be discussing the applications of the ideal gas law, including molar volume, density, and the molar mass of a gas. Solving the ideal gas equation for the volume of 1 mole of gas at STP gives 22.4 liters, which is, if you don't remember, the mole is 6.022 times 10 to the 23rd molecules of gas. So whenever it's at STP, 6.022 times 10 to the 23rd molecules will consume 22.4 liters. The actual gas itself is irrelevant. It's true for all gases. We call the volume of 1 mole of gas at STP molar volume. It is important to recognize that 1 mole of the different gases have different masses even though they have the same volume. So when we look at this picture here, notice that every single canister is saying 22.4 liters for 1 mole. However, the actual molecules are different. For instance, this one has helium and this one has xenon. Xenon is far heavier, but it still contains the same amount of mass, or same amount of volume. CH4 has multiple atoms, but because the distance between the molecules are so great in comparison to the molecule themselves, it's still going to be 22.4 liters. So we can use this in stoichiometry like we have with previous questions. So how many liters of O2, so we're looking for liters of this, at STP can be made from the decomposition of 100.0 grams of lead 4 oxide. So, first thing we need to do is figure out our plan. We're going from one compound to another, the horizontal line. Moles are the end caps to the horizontal line with coefficients above for the conversion factor. From grams to moles, we're going to use molar mass, which it tells you right here is 239.2, so we don't have to calculate it. If you needed to calculate it, you'd have to look on the periodic table to determine the molar mass of the lead and the oxygen and add them all up. Now to go from moles to liters, we're going to use that 22.4 liters per mole number that we talked about in the previous slide. And from here, it's just a regular stoichiometry. 100.0 grams PbO2 over 1. We have grams on top, so we're going to put grams on the bottom. And the molar mass that goes with it, 239.2. And that is equal to 1 mole on the top. We have moles of PbO2 on the top, so we put moles of PbO2 on the bottom. And then now we're here, and we're going to be using coefficients to get here. So the coefficients of PbO2 is 2, and then there's 1 mole of O2, because the coefficient is an invisible 1. Now this time, it's asking for liters. So moles are on top, we want to put moles on the bottom. 1 goes with moles. And then 22.4 liters will be on top. Remember, what you're looking for will be on the top of the last bracket. So 100 divided by 239.2 divided by 2 times 22.4, 4.682 liters. There's 4 significant figures here, so we want to have 4 here. And this is of O2. So let's move on to density. We're relating density to molar volume because of the fact that density is a ratio between mass and volume. Density of a gas is generally given as grams per liter. So the mass of 1 mole is the molar mass, and the volume of 1 mole at STP is 22.4. That means the density would have to be the molar mass over 22.4. Think of it this way. Molar mass is grams per mole. Liters is molar volume, it's liters per mole. The moles cancel, and we're left over with grams per liter. So this is a really easy step to figure out the density of nitrogen gas at STP. First thing we need to do, we know density is molar mass over 22.4. So that means we need to figure out the molar mass of N2. So that's 2 times 14.01, which is equal to 28.02 grams per mole. So the molar mass is 28.02 grams over 22.4 liters, and that gives us 1.25 grams per liter for the density. Now this is a little bit more complicated. We're going to take the density and the molar mass and try to figure out how we can rearrange the question to figure out how these two things are related. So we know that density is mass over liter, and the moles is mass over the molar mass. We know that by the previous questions. For example, 100 grams, we had the molar mass on the bottom. Well, that turns out to be mass over molar mass, and that's where this is coming from. So if we think about it that way, PV is equal to nRT, we can put this information into N, so it's PV is equal to the mass over the molar mass times RT. Now, because of mathematics, when it's divided by the molar mass, that means all of this is divided by the molar mass. So PV is equal to the mass times R times T all over the molar mass. We also know that density is equal to the mass over the volume. Well, we have mass here and we have volume here. So we can rearrange this equation then to have mass over volume. So if we say P is equal to mass times R times T over the volume times molar mass on the bottom, because I've divided both sides by V, we notice that we have mass over volume here, which is the same thing as density. So that's saying that we can substitute P is equal to the density times R times T over the molar mass. And if we were looking for just the density, we can rearrange the equation one more time to figure it out. So we're going to cross multiply pressure times molar mass. I'm going to abbreviate that to just be mm. And we're going to divide both sides by RT. And that's going to give us the density of a gas. So we can figure out the density of a gas without even knowing the mass, or the volume for that matter. Alright, so let's try to do this. So density, we'll rewrite our equation up here, is equal to the pressure times the molar mass over RT. Remember, T is in kelvins, R is 0.08206 atm liters moles kelvins. Pressure then needs to be in atms, and then molar mass is going to be grams per mole. So we're talking about N2 again. Calculate the density of N2 at 125 degrees Celsius in 755 millimeters of mercury. So we need pressure, the molar mass, R, which is 0.08206, and temperature. So pressure is 755 millimeters of mercury. However, if we look at our constant, we see that we need it in atms. So we have to divide it by 760 millimeters of mercury. And that equals 0.993 atm. The molar mass of nitrogen is 2 times 14.01 from the periodic table. that's 28.02 grams per mole. And then the temperature is 125 plus 273, which comes out to be 398. Now we can just plug these numbers in to figure out our density. So density is equal to 0.993 atm. The molar mass is 28.02 grams per mole. R is 0.08206 atm, liters, moles, kelvins, and then temperature is 398 Kelvin. So the kelvins cancel, the moles cancel, the atms cancel. We're left over with grams and liters. So that equals 0.852 grams per liter. Alright, let's try that again. This one's a little bit more difficult. So we're still using the same equation. D is equal to the P times the molar mass over the R times the T. So let's write out our units we need. So, calculate the density of a gas at 775 torr. So that is our pressure. We need to convert that to atms before we do anything else. And that comes out to be 1.02. Molar mass is the part that's difficult, but let's wait for that. And 27 degrees Celsius plus 273 will give us 300 Kelvin. Our R is 0.08206 moles kelvins. Alright, so we have 0.250 moles weighing 9.98 grams. We don't know what compound it is, so we can't figure out what the molar mass is. However, we do know that the unit for molar mass is grams per moles. And we know that this particular sample is 9.98 grams in 0.250 moles. So we can figure out the molar mass by dividing those two to be 39.9 grams per mole. Alright, so now we can start our equation. D is equal to 1.02 times 39.9 grams per mole over atm, liter, moles, kelvins, 300 Kelvin. What cancels is atms, moles, kelvins. We're left over with grams and liters. And that comes out to be 1.65 grams per liter. One of the methods chemists use to determine the molar mass of an unknown substance is to heat a weighted sample until it becomes a gas, measure the temperature, pressure, and volume, and then use the ideal gas law to figure out the molar mass. We can do this in this question. Calculate the molar mass of a gas with a mass of 0.311 grams, has a volume of 0.225 liters, and a temperature and pressure of 55 degrees Celsius and 886 millimeters of mercury. So we're going to go back to the regular PV equals nRT. Let's get our R ready, so that way we know how to match up the rest of our units. Okay, so 0.311 grams. Remember previously when we were trying to figure out the molar mass, we said if we took the grams over the moles, we can figure out what the molar mass is. Well, we can figure out the N, we can figure out this equation, because it's going to be 0.311 grams over whatever N is. Alright, so pressure is 886 over 1. Gotta convert that over to ATMs. And that comes out to be 1.17. Volume is 0.225 liters. N is what we're looking for. And temperature is 55 plus 273 because we need it in kelvins. So let's go ahead and plug our numbers in. 1.17 ATM times 0.225 liters is equal to, our question is N, 0.08206 and our temperature is 328. That comes out to be 0.00978 moles. Now we can figure out our molar mass by taking our initial number of grams, 0.311 grams, dividing it by the molar mass, and that gives us grams per mole, and that's 31.8 grams per mole. We're going to do one more practice problem dealing with the molar mass. What is the molar mass of 12 grams? So we're going to use this at last. That's going to be our final thing. Occupies 197 liters, 3.80 times 10 to the second torr, and 127 degrees Celsius. So we need to convert our pressure times 10 to the second torr. We're going to divide that by 760 to get into ATMs. And that comes out to be 0.500 ATM. Our temperature needs to be converted as well. 127 plus 273 is equal to 400 Kelvin. The other units are fine. So 0.500 ATM, volume is 197, equals X, because that's what we're looking for, because then we can use it in the molar mass. 0.08206 ATM, liters, kelvins, moles, and 400 Kelvin. The kelvins can cancel, and we get, when we multiply and divide, we get 3.00 moles. The ATMs cancel and the liters cancel. We're left over with moles. That's supposed to say moles. Alright, so to determine the molar mass, 12.0 grams, which is coming from our initial question, divided by 3.00 moles, is going to equal 4.00 grams per mole. And this is explaining how we're using ideal gas law for other applications.